Okay, this meeting of a cold and warm front produces a special type of front known as occluded front. Cold air, when you think of cold, perhaps it's slower. After all, you can catch a cold pretty easily. You don't catch a hot. But actually, the cold front in our extratropical cyclone system is moving faster than the warm front. Warm front gradually sloping up over the colder air. Cold front steeply sloping up the cold going under the warm there. With the cold in moving more vertical, faster, and so it can catch up. And we get this. The warm air is not reaching down to the ground. Occluded means blocked. And so our occluded front is referring to the fact that we've got a front here that isn't present down here. So this warm air up here, it's gradually getting squeezed in, shrunk, and the water vapor in there is cooling down. We're going to be reaching the dew point, making clouds, and possibly, if it's unstable enough, making rain or even stormy conditions. So on a weather map, here's what it looks like. We have the cold front, our blue with triangles, warm front, our red with the half circles, and this purple mixed one is symbolizing the occluded front, where it's partly the cold front, but up above the cold front there's a warm front not touching the ground. So we've got warmer air here, and warmer air will typically have more water vapor in it, cooler air, and then our coldest air here. And this difference in temperatures is giving us the energy causing the low pressure cyclonic system. Okay, so here's comparison. Again, energy source for a tropical, warm water vapor evaporating from a warm area of the ocean. Extratropical, it's those differences in temperature side to side that set up our system. No fronts with our tropical one. If a hurricane runs to a front, that's generally a problem for the hurricane. Extratropical, we have warm, cold, and occluded front coming together. Tropical warm core, extratropical cold core. Pressure down the surface, of course, is low, as with any cyclonic system. But up at the top of the troposphere, the tropopause, we've got higher pressure for the tropical, but lower with the extratropical. Wind speed is fastest close to the ground in our tropical systems, at the top of our extratropical system. And again, we need warm water to make our tropical cyclone. Our extratropical one could be anywhere. Although hurricanes tend to get bigger publicity, there are some well-known extratropical ones. Sandy, 2012, major damage, like pictured here, to the New York City area. It had been a tropical system, but New York City, it's far enough north, the water there is usually cooler. And so as it moved over cooler water, it changed into an extratropical system and then ran into New Jersey, New York City, major flooding and damage to the area. A very famous one over the other side of the Atlantic in Great Britain, the Great Storm of 1987. This, again, was an extratropical cyclone. And right as it approached England, it strengthened rapidly. The weather forecast just before it had announced that it didn't look very bad. And that was the last report on it that most folks got until it hit, and it was bad. So, did not help the Weather Service's reputation there. More recently, we had Ophelia was a tropical system out in the middle of the Atlantic, and as it moved out away from the equator, as hurricanes typically do, it crossed over into cooler water and changed and became an extratropical system and hit Ireland. Record wind speeds there. One that may be famous for those of you who are into some areas of more country and folk music. November 10th, 1975, there was a very severe extratropical storm on the Great Lakes. And with this storm, bad weather, bad news for ships out on the lake, and one in particular was sunk, the Edmund Fitzgerald, and a popular song was made about it. Okay, from that we'll go to a little bit on how do you forecast the weather. There are quite a few methods out there that can be used. What information do you have? Also, how much does it matter? If I'm wondering, do I think I need my raincoat tomorrow? That's not quite as critical that I really get into detail. But a forecast for weather that might affect something of much more general importance, that's going to be done a lot more carefully. Different forecasters will have some different aspects that they prefer, models they favor, things like that. Of course, this is changing quite a bit with development of technology. This is usually helpful, but we do see some problems as well, things that may not be quite as effective in helping with the forecast. For one thing, if some of the information is not popular, studies on climate change, for example, they show the climate is changing. Things are getting warmer. Folks that don't like that or try decreasing our weather information, which is not very helpful. Of course, it also kind of says something about whether they think that more information is going to support their position. Another challenge, some of the radio frequencies that are used to transmit weather information provide warning of hurricanes, things like that. Oh, but we need more bandwidth so that folks can play bigger games faster on their phones. And of course, that'll make money, and warning people about hurricanes, all that does is save lives, so what's our priority here? What are some of these critical technologies telling us about weather? New sources of information. Satellites give us big pictures of basically all over the world. In my mother-in-law could remember, as a child in South Florida, all the birds left the beach. Better get ready. It's coming. That was your advance notice. Not very long notice. Satellites, doesn't have to be a ship out there on the ocean or airplane to see it. Satellite will pick up on things. Airplanes, of course, very useful as well. Again, they cover a lot more area than ground-based or ship-based observers could, and allow you to actually get into the weather and check things out as long as it's safe to do so. It can be risky. One of the Hurricane Hunter planes that went out to check on Hugo discovered that Hugo was a lot stronger than they expected and nearly hit the ocean. But it does provide quite valuable data. One of the first technologies used, weather balloons. Sticking thermometer up on balloon, getting measurements, things like that. And weather stations. We've got more places where people have measurements they're taking to record data on the weather and put that into our modeling of what the weather is going to be like. Using different ways of seeing. Visible light, that's quite useful, of course, but I see clouds. What's behind the clouds? Well, other parts of the electromagnetic spectrum can go through the clouds and give us other pictures there. Infrared is quite useful at detecting what areas are warmer or colder. Very important aspect. Measuring temperature, wind speed, all these good things are important bits of data to go into our weather measurement. Radar uses radio waves, and these can bounce off things, including water droplets in the air, measure clouds or rain, things like that, and tell us what's out there. Of course, you can also use it to detect airplanes and ships and things like that, but for weather, we're focused on the clouds. Now, there are yet other things in the air. Radar detects, for example, this time of year, migrating birds and insects. So the weatherman has to figure out whether that's a cloud or a bunch of bugs. That gives you somewhat different things there. A newer specialization on radar is the Doppler radar. This not only says, is there something there, it also will tell you, is it moving towards or away from you? So basic idea, you're sending out your radio wave signal and then listening for echoes. And you can get pictures here, such as velocity. Are things moving towards you or away from you? And if, like in the picture here, some's moving towards, some moving away, how do you get that? If it's spinning, which could potentially be a setup towards having tornado. Reflectivity, that's how much is bouncing back, which shows you basically how big those raindrops are, maybe even some hail, stuff like that mixed in. Electronic meters, of course, we use them in lab. You've encountered those bits, so those are convenient ways of measuring a lot of aspects of the weather. Remote reporting. We can have a station set up somewhere out in the middle of nowhere, and it sends off a radio signal from time to time to give the results. And so that's a good way of covering a lot of area that it's not practical to have a weatherman on site all the time. Now, of course, finding a good spot for it. I heard a story about, it's actually a seismometer for earthquakes rather than a weather station, but this old building looks like a good spot to stick our seismometer in. Shouldn't bother anybody. And then they come back to find a big crowd, and the bomb squad's about to blow up the seismometer. Folks were using that building and didn't know what this thing was and were alarmed. So yes, you do need to make sure you've got it properly identified there. Of course, Dr. Jones has a story about problems associated with setting up remote monitoring stations, and somebody was going around stealing the batteries out of them. They put up a sign warning that the batteries had radioactivity and you should head for the hospital if you feel any of these symptoms. And somebody showed up to the hospital worried about radiation sickness. Okay, here's our battery thief. Calibration is a challenge. Okay, we're getting the radar. There's rain out there. How much rain? Well, you have to actually do some direct measuring and compare that to your radar signal to get good calibration there. All areas of science have been dramatically impacted by the vast improvements in computer power over the past several decades. Computers can analyze much more data at once than an individual can, and put that into a much bigger, more complicated picture to tell us about the weather.